Let's talk about this. The paper that Schrödinger wrote from the fundamental perspective, how he approached the Schrödinger equation and what are the progress he made uh, to build such a very complex machine.
When Schrödinger approached his famous equation, he was trying to describe quantum systems in a continuous way. Inspired by Louis de Broglie's wave-particle duality, he imagined particles as wave functions whose evolution in time could be described by a differential equation. He built on classical energy expressions, translating kinetic and potential energy into wave terms. His work gave the foundational framework for modern quantum mechanics, letting us predict quantum behavior. And it was a major turning point in understanding nature at the smallest scales.
So, so you mentioned about this energy expression. What was that, and how it connects?
Schrödinger started from the classical total energy expression, kinetic energy plus potential energy. For a particle, the kinetic energy is the momentum squared divided by twice the mass. He replaced the momentum with an operator related to how the wave function changes. The potential energy stayed as a function of position. This combination gave a differential equation that describes how the wave function folds, linking quantum states to measurable energy.
What do you mean by that, linking quantum states to measurable energy?
In quantum mechanics, the wave function contains all the information about a system's state. Schrödinger's equation shows how that wave function changes with time. When you apply certain operators, like the energy operator, you can extract measurable values, such as energy levels. So by solving Schrödinger's equation, you bridge abstract quantum states and actual physical quantities we can observe in experiments.
So, what was the smallest scale you are talking about?
We're talking atomic and subatomic scales, distances on the order of angstroms or nanometers. For context, an atom might be about 0.1 nanometers across. Schrödinger's equation captures the behavior of electrons and nuclei at these tiny scales, so we're really dealing with the realm where quantum effects dominate.
So, what problem actually he was thinking, and how he arrived that he can solve that problem?
Schrödinger was grappling with how to describe particles like electrons in atoms after de Broglie suggested particles behave like waves. He wanted a wave equation that could predict stable energy levels in atoms, especially the hydrogen atom. After exploring analogies with classical wave equations and energy conservation, he realized a second-order differential equation could capture the wave nature of matter. By matching his equation's solutions to known atomic spectra, he confirmed it worked, and it became a cornerstone of quantum mechanics.
So, he was describing particles like electron in atoms. Okay, after de Broglie suggested particle behave like waves because it has lambda associated with. So he wanted wave equation that could predict stable energy levels in atoms. That was very big point, stable energy levels in atom.
Yes, those stable energy levels are crucial. They explain why atoms emit or absorb light at certain frequencies and why matter is stable at all. Schrödinger's wave equation captured those discrete energy states like the hydrogen atom's energy levels, making it possible to predict atomic spectra. That was a breakthrough for understanding how quantum systems behave.
Then what did he realize? Second order differential equation could capture the wave nature of matter. How did he arrive that part?
He drew from classical wave equations like those for sound or light and saw that a second order equation naturally describes waves. By replacing momentum with a wave operator, he connected energy and wave properties. When applied to the hydrogen atom, the predicted energy levels matched known spectra, showing that the wave nature of matter was captured by this equation.
So when applied to the hydrogen atom, the predicted energy level matched the known spectra.
Exactly. When Schrödinger solved his equation for the hydrogen atom, the discrete energy levels it predicted matched the spectral lines scientists had measured. That was a powerful confirmation that his wave based approach described reality at the atomic scale.
But how did it connect with the atomic scale picture? And do we already have the hydrogen atom solution at that time?
At that time, people knew the hydrogen atom's spectral lines, but they came from empirical data and early quantum models like Bohr's. Schrödinger's equation provided a deeper theoretical foundation. By applying his wave equation to the hydrogen atom, he derived those same energy levels from first principles. In other words, the atomic scale picture suddenly had a fundamental wave equation explaining why those energy levels exist.
So atomic scale picture suddenly had a fundamental wave equation explaining why those energy level exist.
Exactly. Schrödinger's equation gave us a universal mathematical framework that naturally explains why atoms have discrete energy states. Instead of relying solely on empirical observations, we now had a fundamental wave based theory. It laid the foundation for all quantum chemistry and modern atomic physics, showing that these energy levels are a natural consequence of the wave nature of matter.
How did he suddenly connect with the second order differential equation part?
The connection came from the analogy with wave physics. Classical waves, like sound or light, follow second order differential equations. Schrödinger realized that if matter had wave properties, thanks to de Broglie, then a second order equation in space, paired with time evolution, could describe particles. By inserting the right operators, he turned classical energy relationships into a quantum wave equation. And that became the famous Schrödinger equation.
So that was very beautiful line that you talked about. That he realized that matter has wave properties, and that de Broglie confirmed. After that, the second order differential equation in space paired with the time evolution could describe particles. By inserting the right operators, he turned classical energy relationship into quantum wave equation, and that became the famous Schrodinger equation. So that was the whole motivation, and this was a bit of intuition, but how actually he write down the correct Schrodinger equation, and how did he verify that part?
Schrödinger started by looking at the classical energy expression, kinetic plus potential. He replaced momentum with an operator that involved how the wave function changes in space. That led to a second order differential form. He tested it on the hydrogen atom, where earlier models gave known energy levels. When his equation gave the exact same results, like the observed spectral lines, it was a clear verification. That consistency showed he'd found the right equation.
So he was looking classical energy expression, kinetic plus potential. He replaced momentum with an operator that involves how the wave function change in space. This led to the second order differential form. He tested it on hydrogen atom where earlier model gave known energy levels. When this his equation gave the exact same result like the observed spectral lines, it was a clear verification. But that was good, but uh, he replaced momentum with an operator that involved how the wave function changes in space. Can you support this line?
Absolutely. In classical mechanics, momentum is mass times velocity. In wave mechanics, de Broglie linked momentum to wavelength. Schrödinger translated this into a differential operator. Momentum became related to how the wave function changes with position. Mathematically, this is a derivative. He used the momentum operator as a derivative operator scaled by constants, and that gave him the form that ultimately led to his equation.
So classically, momentum is mass time velocity, P is equal to mv. Then in wave mechanics, momentum is linked with the wavelength. So Schrödinger translated this into a differential operator.
Exactly.
Why differential operator they need?
The differential operator was needed because a wave is defined by how it changes. In quantum mechanics, the wavelength tells you how the wave function varies in space. By using a derivative, Schrödinger could encode how the wave function's shape, its curvature, relates to the particle's energy and behavior. In short, that's what lets waves describe particles in a meaningful way.
So mathematically, this is a derivative. Okay, then the wavelength tells you how the wave function varies in space. By using derivative, Schrödinger could encode how the wave function safe is curvature relates to the particle's energy and behavior. So wave function safe, its curvature relates to the particle's energy and behavior.
Yes, precisely. The curvature of the wave function, essentially its second derivative, ties directly to kinetic energy. When you add potential energy, you get a complete picture of the particle's behavior. Schrödinger's insight was that this wave equation, linking curvature and energy, describes the allowed states of particles, giving us the foundation of quantum mechanics.
The curvature of the wave function, what do you mean by that part?
When I say curvature, I mean how the wave function bends or changes as you move along space. Mathematically, it's the second derivative, how the slope itself changes. In Schrödinger's equation, that curvature is tied to kinetic energy. When the wave function curves more, it corresponds to a higher kinetic energy. So, in essence, the curvature reflects how the wave wiggles and what energy states are possible.
So essentially, it's directly to the kinetic energy. When you add potential energy, you get a complete picture of particles' behavior. Can you support this line? When you add potential energy, you get the uh, complete picture, particle behavior. And how does here wavelength also play a role?
When you add potential energy to the equation, like an electron's attraction to a nucleus, along with kinetic energy, you get the total energy. The wave function's wavelength is related to momentum. Shorter wavelengths mean higher kinetic energy. The balance between kinetic energy, linked to curvature, and potential energy, linked to position, determines the stable allowed states. So wavelength, through momentum, helps set the particle's energy, shaping the wave function's form and the particle's behavior.
Wave function's wavelength is related to momentum. Okay, shorter wavelength mean higher kinetic energy. The balance between kinetic energy linked to curvature and potential energy linked to position determines the stable allowed state. So wavelength through momentum helps set the particle's energy, shaping the wave function's form and particle behavior.
Yes, exactly. In short, the wavelength is tied to momentum, and momentum is tied to energy. Thus, when we solve Schrödinger's equation, the allowed wave patterns, those stable states, reflect the particle's total energy. In other words, the wavelength via momentum tells you what energy states are possible, shaping where the particle can be and how it behaves.
So when we solve Schrödinger equation, the allowed wave uh, patterns, those stable states reflects the particle total energy. In other words, the wavelength via momentum tells you what energy states are possible and shaping. Okay, what energy states are possible? That is also we are getting through Schrödinger equation for a quantum system. How, why we are only getting allowed energy states, why not other parameter?
The reason we get only specific allowed energy states is that the wave function must meet boundary conditions, like being smooth and finite. Just like a string fixed at both ends can only vibrate at certain frequencies, a quantum wave can only form patterns that fit the system. These patterns correspond to discrete energy levels. Other parameters, like position, are continuous, but energy states emerge quantized because of these constraints.
So wave function must need boundary conditions. Why boundary conditions are very useful?
Boundary conditions are essential because they ensure the wave function is physically meaningful, like not shooting off to infinity. They basically set the rules of the game, dictating which wave patterns can exist. Because the wave has to fit these conditions, like being zero at the edges of a box, it limits what solutions or energy states are possible. In other words, boundary conditions give us those neat, discrete, allowed states.
Discrete allowed state, what do you mean by that part?
I mean that instead of any random energy value being possible, only certain specific energy levels are allowed, almost like steps. The wave function can only form stable patterns at these exact energies. So the particle chooses from a discrete set of energy states rather than a continuous range. That's what we mean by quantized states in quantum mechanics.
What do you mean by quantized states in quantum mechanics meaning here?
In quantum mechanics, quantized states means that certain physical quantities, like energy, can only take on specific discrete values rather than any value. It's like a staircase, where you stand on particular steps, not in between. For example, an electron in an atom can only occupy certain energy levels. That's why we see distinct lines in atomic spectra. Each line corresponds to a quantized energy transition.
Do they also connect with the allowed energy levels or orbit, elliptical orbit inside the atom?
Yes, they absolutely connect. Those allowed energy levels correspond to specific orbits in early atomic models, though we now understand them as quantized wave states, not literal elliptical orbits. Each energy level represents a stable wave pattern where the electron's probability cloud forms. So what Bohr initially saw as distinct orbits, we now know are quantized energy states, directly linked to the Schrödinger equation's solutions.
Okay, then what was the first evidence they found out that there are quantized energy state and there are discrete energy levels, allowed energy levels?
The first strong evidence came from atomic spectra, especially the hydrogen atom. In the late 19th century, scientists saw that atoms emitted or absorbed light at distinct, discrete wavelengths. Balmer and then Rydberg found mathematical patterns in these spectral lines. Later, Bohr's model explained these lines as electrons jumping between quantized energy levels. Schrödinger's equation later provided the deeper wave-based explanation for why those discrete energy states exist.
Okay,
I'm glad that helped connect the pieces. If you ever want to dig deeper into any part of it, just let me know.
okay, can you make conclusion what we have discussed? What was the very useful things we discussed in this?
So, to wrap it up, Schrödinger tackled the idea that particles behave like waves. By translating energy into wave terms, he built his equation. That equation explained why atoms have discrete energy levels. We discussed how momentum became a differential operator, why boundary conditions force quantized states, and how those states match the spectra we observe. In short, we explored how Schrödinger gave us the key to understanding the quantum world.
Okay, thank you.